here in the US, they're radio, but maybe that's going to change, right? Anybody studied distributed generation and how it's going to change everything? Because we don't even know how we're going to protect circuits or where we have all the multiple sources and all the different feed-ins together in the grid. So if we develop a medium voltage network, maybe these devices have a big play there. Might need to be scaled down, but the technology might be very applicable. So improving renewable integration, and I'm going to show you 3 use cases that are in progress. Some have been deployed, some are still ready to be deployed. Next. All right, the first one, this one, UK Power Networks. Once again, there's always one line that loads up first, and if you see it there, kind of, and this is really because of the distances in the past. So you had a 24 kilometer mile line, a 19 kilometer mile line, and a 28 kilometer line. So which one you think are going to load up first, the short ones or the long one? Short ones, the short ones. And when they loaded up, that limited the transfer capacity from all the renewables out on the coast up to the load centers. So next, click one more time. So they were putting in the conventional Guardian technology on the 2 shorter lines, and kind of as I'm an old utility guy, so you know what utilities do when something new comes out? They have to do a pilot. That's just, it's in the Big Ten as utilities. You got to do a pilot first before you implement something. So I think this might have been their pilot case. So they implemented the Guardian technology on the 2 short lines and allowed up to 95 additional megawatts transfer from generation to the load center. Next slide. So 95 megawatt, 8 million pounds. Is that a lot of money? I don't know. Pounds are heavy. Yeah. And but as conditions change, those could be moved to other places. So there's the first one, solar connections. Another renewable energy case. This one is, you see where it is? Australia. Evidently, they got some good connections down in Australia. And once again, it deals with renewables. You see all the nice wind farms out there. Electronet, and they also had a problem with a very short line here that loaded up really quick and limited all the power flow from the generation to the load. And they decided to put the Guardian solution in on the short line and try to increase the impedance of the line to force the power flows onto the adjacent lines. Next slide. And this has both 132 and 275 kV lines in the grid. And they were able to scale it up. Next slide, I think it's got the conclusion. Added, 20 megawatts and saved about 1.3 Australian dollars in fuel costs by getting the renewable energy into the grid, and got 150 megawatts of incremental resources there. So there are particular use cases that kind of stand out, and utilities, like once again, each utility, they could look at, okay, everybody else has done a pilot, I should be good. No, they got to do their own pilot. That's just one of the rules. So there was one for Australia. I think I got one more from Australia. Next slide. Yeah, same continent, right? And this one, 330 kV lines, and this is, I think, this is still in process. They've done the planning studies by implementing smart valves on these 2 lines, 1 and 2, and using the new technology for this one. Next slide. And this one, they can operate these real time, and this mentions that one of them is really kind of put there to kind of do the control, and then the other one goes plus minus based upon the real-time flows of the network. So these do come into the operator console and definitely have control set points to kind of keep you within the range. but they allow the operators to fine-tune their network. Wouldn't it be nice to have little knobs out there on all the transmission lines? Wow, that's kind of the future. One more click and it'll give you the, I guess from the study, they can talk about up to 80 megawatts of network capacity, but up to maybe 180 in the future. And these are not insignificant. This is big dollars, big bucks. And the devices, you know, what's that device worth? What's a smart valve worth? It's worth more than the parts, right? What it can do for you. So I'm not in marketing or in sales, but they probably try to come up with a price that kind of equates to the value that it gives to the utilities and still offers them an advantage. So we're going to be stuck on this slide until the food comes in, right? We've waited long enough and the pizza's here. So yeah, hit the down button one more time. We're getting close since the pizza's here. Summary slide, awesome. That's good timing. Okay, had you heard about power flow control before? Is anybody talking about this? This is kind of new, isn't it? Yeah, and it's new to utilities. And utilities are slow to move. We're, how do you say, conservative. So that's one of the issues Smartwires has been working on since 2010 of getting utilities to adopt change. This is a big change for them, and it can have a big impact as people become aware of it. Next one. Our partnership working together. I mean, obviously we helped a lot with the designing to withstand all of the conditions that utilities have to deal with, which a new manufacturer wouldn't know about that. So. And we also got a lot of feedback from utilities into them in their initial product development. And truth be told, they've hired a few of our graduates that have joined their R&D team. And they've got like, it's over 200 engineers now working on this around the world. So they've come from a startup that we kind of helped launch in 2010, and they're about ready to turn up. Next one. And you've seen the growth in the technology from the very simple concept that we helped them put together and pilot all the way to the smart valve, which has a whole lot more capabilities and a whole lot smaller footprint. And once again, I know nothing of the price of this technology, so don't ask that question. I don't know what it costs, but it shouldn't cost that much, right? Next one. And we will continue to kind of collaborate with our members. As I said in my opening comments, everything is changing, and we have to figure out how to integrate all of the renewable generation that's coming onto the grid, both in the community, at the customer level, at the medium voltage level, and then the large farms. And I'm also working with the Center for Distributed Energy, DPAC Center, and we're working a lot on advanced technologies. We have projects from ARPA-E on the power electronic transformer, which we'll be testing over there in Charleston. We also have a new project with Sunshot from DOE to develop basically a medium voltage string inverter to take the solar farm from like 2000 volts DC directly up to medium voltage to eliminate the 480 volt step in transformers. So we see a whole lot of impact here, and thinking about it, what a great time. Boy, that pizza smell is rough. So everybody is ready for more discussion. I think that was it. So let me open up for questions, and if I don't know the answer, I will ask Randy. Right?
I'll just ask it on the test.
Okay, yeah. Any easy questions for old utility guy? Yes.
Frank, I'm not a transmission guy, but what does this do to your transmission relay?
It impacts it. Once again, we designed the device so that if there is a temporary or permanent fault, as it's looking at the shape of the waveform, when that current starts to go up, it detects the rate of change is rapid, and that thyristor pair, the smart bypass, basically seals the device, and it's as if it wasn't there. So the same relays can work with this technology.
How about where you have, the distance relays that,
Right.
power is using the.
Exactly.
look out 20 miles and-
If they're in service, it's going to give false readings because it makes it think the line's longer. But if there is that rapid rate of rise on the current to show you that there's a fault coming, then they're bypassed. So that's the basic principle. Now, will there be new relaying schemes that probably work with these? Maybe, yeah. But we tried to take it from that approach as do no harm. Let's get them out of the circuit if there's any disturbance. And that's the way they're designed now. Good question. All questions are good. Yes?
Since you are changing the impedance of the line to change the power flow, what happens to the power loss in the system?
The power loss, obviously if you're adding impedance, there's a little bit, but these devices, we did basically monitored the heat of them. They're not glowing. It's really dissipated. You are dissipating a little extra heat because of the added impedance, but it's well within the design of the product. But yeah, that's in the noise. Good. Other? Yes, Randy.
Okay, so I'll ask you this, so that those that are in my class are taking notes.
Yeah,
that they,
this will be on the quiz.
will be on the final
Right.
exam.
Yeah.
I guess I'm going to ask about the Guardian, but I think this is applicable to the Smartwires as well. You mentioned earlier about tying it in with SCADA and whatnot, but the Guardian devices were standalone. Is that
That was the intent. That first pilot at TVA, we put in a packet-based radio system, so they were able to monitor each one individually on SCADA, more for, I want to keep an eye on them.
Yeah, well, because my question is this: how does, if you're, you get a line and it goes up to X%, loading, and you're trying to reduce it, how does the device know whether it needs to be in the circuit or not?
Right.
How does it know what it's loading?
The simple approach is it's a set point controller. You program them and, okay, here's the maximum thermal limit for the line. And you maybe have two stages. Half of the units come on when you hit this number, and then you have the other half come on there. Those are fixed. And you would have to go back out probably with a point-to-point radio link, then change the set points.
Yeah.
So that's the old approach. The smart valves, and a lot of those, they want them real-time on SCADA as a knob. They want to control plus-minus injection.
Yeah. So they're all talking to each other and adjust to.
They have
So if you insert impedance in this line and the power does this, they know what happens rather than.
Right. Well, that last case that I showed you from Australia, that's their design. They have one that kind of regulates things, and the other one they use to balance that kind of as a secondary control. So each, as a planning engineer, I mean, you're going to have. They do, as a part of that 200 cadre of engineers, they've hired some experienced planning engineers from utilities that can run these use cases and run all of those things, because you have to know all the parameters up front to decide where to put them and what to put, so that you have the flexibility to do the plus minus injections to get the desired outcome. So in that say, it's not one size fits all. It does take planning studies of your network and looking into the future projections of load to really come up with where you put them and what you put. So we're going to need all of y'all as new engineers to go do that, right? Assuming they graduate.
Assuming.
Yeah. I'm sure they were paying attention.
Yeah, the answer is knob. Turn the knob.
Turn the knob. Down, up. I got that. Now, nobody knew about this before you came, right? No. Okay, so it's new. It's new, and I think it's going to catch on. They're to the point now of ramping. Anything else? Yes.
How exactly, how big of a role does this play in solving the multiple source renewable problem that's happening?
Depends on your particular set of circumstances, your particular grid. It's a it depends answer. If you were a utility that just overbuilt you know, and that don't have line limitation capacity problems, then you don't need this.
Okay.
You know, but what I'm telling you is that last part, you know, the way we make it, move it, use it, sell it. The other thing that's changing, Hawaii has fired the first shot. They've announced to the nice people in HECO, Hawaii Electric, that they're no longer to be able to make money based upon what they spent. Now that's yet to be determined what that new model is going to be, and it's not one size fits all. Every state has its own regulations, but knowing how regulators talk, I don't think it's going to be long before that message gets to Georgia, to South Carolina, that, okay, well, you don't have a guaranteed rate of return anymore based on what you spend. This is a competitive marketplace because, you know, those new solar farms, they're not necessarily owned by the utilities anymore, right? There's private players out there. Everything's changing. So stay tuned. That help? But yeah, if they've overbuilt, it's, yeah. But you're going to have to study your particular circumstances to decide if this solution works for you. But a lot of cases, it might. It might. It's a new tool in the toolbox. And it certainly promotes integration of renewables now at a critical time. Because, you know, some utilities will say, no, we can't give you an interconnection there. Our grid won't handle it. Right? That's a typical response. Or you're going to have to pay to build a line from here to there. No, here's another solution. And that's coming. That's coming sooner rather than later. So y'all going to help? Yeah. Sure, you need a job. Right? That pizza smell is overpowering, yeah. You think you got enough? We'll find out. Anything else? Is it time to eat pizza? Cool. We got 4 minutes.
Yeah.
Yeah.
So Frank. So guys, you know, I'm not going to pitch PES, but if you want to know like what you can get out of PES.
Oh, I was going to talk about that next time. I mean, I've got more slides if you stay for pizza, right?
Yeah, and you can talk to him. So that's what PE is about, the people. So we have so many wonderful people, networks, to, you know. So.
Are some of y'all leaving after this? Can I give one minute pitch? And I'll show you in the slides, but we've got like out of the 420,000 IEEE members, like 117,000 of those now are students. Wow. And a lot of us old guys, there's, you know, we're particularly power people, you know, there's new guys and old guys, there's no middle guys. So there's a huge opportunity there. But the message I'd like to get across to students is that you need PES. Why do I need PES? I'm graduating, right? I don't have any professors making me come here to a meeting. What are you going to need when you get out?
Networking.
Networking. It's another kind of networking. When I graduated, I picked a company for life. I was half right. I ended up with 2 companies, Georgia Power, Georgia Tech. That was close. How many different companies are you going to work for? More. I know it's more. My son is on his 5th, right? And he's only 40. So I think I was on the school board back in the early 2000, and we went to a school board venture, and they said the average student is going to work at 7 different careers. I said, no way. It's happening. It's happening. More now than ever, you need a professional network so that you know people around in other companies, because something's going to change. You're not going to be happy. Somebody's going to buy out your company, and they're going to do all that stuff to you. You need that professional. And we had a young professional come to the student congress that we had last August in Sao Paulo. He's a young professional from Europe. The way he explained it was, it's kind of like fire insurance. You know, some of us in here own houses. We have fire insurance. We hope we never need it. But when you need it, and you nailed it. It's that professional network. So, you know, being a PES student member is pretty cheap. The first year is free, and the next year